In the last video, we saw how containers uses overlayFS to layer file system efficiently, but there is a one piece still missing. Right now, we are adding file system on top, but real container don't just add. They replace the root file system completely, and that is done using pivot root. Today, we are going to do exactly that, replacing the root file system just using pure Linux.
Before we start, we need to make sure everything required is available or not in this system. And to check if the command exists in this particular system, we can use which command. So which pivot underscore root. So as we can see, the pivot underscore root is available on this system. Another important thing is pivot root is a privileged operation and we are literally replacing the root file system. So if you're not using a root user or not using a sudo access, you won't be able to perform any operation for the pivot root. So if you're using another user, so you can use sudo -i to change it to the root shell. So now before changing anything, let's see what the system currently looks like. So for that we can use ls/ command. So ls and slash. So this shows the current root file system. So everything in Linux starts from the slash drive and we can see multiple files like bin, boot, dev, etc, etc. So right now this is the real system and every process starts from here. Now let's create our own file system. So for that I have already created one directory, that is pivot root. So let me go inside this. So inside this I'm going to create our own custom file system. So in the previous video we manually copied binaries and the libraries, but in real world scenarios we don't do this manually every time. So now I have automated this using the shell script. So in this particular directory I've already created one shell script. So let me open this, that is build rootfs.sh. So this shell script creates a rootfs structure and also copy the binaries and the dependencies on the specific folders. So whatever binary we required in our custom file system, we can pass the name of that binary in the command line itself. It will automatically copy the binary along with its dependencies to the specific folder. So now let me explain it to you. So first of all, I added a shebang. So this tells the system to run this script using the bash script. After that, I specified the set -e. So if any command fails, the script stops immediately. So this prevents partial or the broken setups. And just after that, I am specifying the variable, that is rootfs. So I am defining a variable so we don't repeat the paths everywhere. And after that, I am creating a multiple directories under the rootfs path. So this creates our mini Linux file system structure, exactly like a container image layout. And then I have added a condition here to check if the binary is being passed by the user or not. So this checks if we pass any commands to the script. If not, it exits with a message along with the usage and the exit code 1. And now comes the interesting part, that is a copy binary function. So here I have created one function, that is copy underscore binary. So here we defined a function to copy binaries dynamically. So here I am looking for the binaries. So for that I use the which command only, the same command which I used earlier to identify if the command exists or not. Similarly, I am using the same approach here to find where the command exists on the host system. And after that I am adding a condition to handle the missing command from the host system. So if the command doesn't exist, it will skip it safely. Then I am copying the binary into the container file system. Right now we are putting everything under /bin for simplicity. And just after that I am running the ldd command, that is to list the dependencies. So it will list all the shared libraries required by these binaries. And then I'm going to filter only the valid library path. And at last I'm going to loop through each dependencies. And after that I am going to copy libraries into a rootfs file system. This is exactly how container image bundle dependencies. And after that we are closing the function. Just after that I am defining a one for loop. So it will loop through all the command passed to the script and calls our function for each command. And at last I am using the loader. It is a very important step. This copies the dynamic loader. Without this nothing will execute. And at last the to echo statement to print done and the command to test the chroot. So now instead of manually copying everything, we are going to use this particular shell script to create our custom file system just like a container file system. So now let's try to run this. Let me come out of it. So as of now there is no rootfs directory in this particular system. So now let's run this script to create a custom file system along with its binaries and dependencies. So let me clear out the screen first and run build rootfs.sh along with bash ls ps hostname mount and the umount command. So I'm going to place all the binaries, that is bash ls ps hostname mount and unmount commands under this particular file system because we are going to use this in our demo as well. So let's press enter here. So now if you see, it created the custom file system. So first of all it copied the binary and then it copied all the dependencies for that particular binary. Similarly it did the same for the ls ps hostname and the mount and the unmount commands. And at last it gave a message that it's done and you can test using the chroot command. So if I run ls here, so as we can see the rootfs got created. And if we are going to see the structure for the same, so tree rootfs So tree command is not there. So let's run ls only. So ls rootfs. So as we can see, it created a complete directory structure for our custom file system. So we just pass the command we want inside our container and the script builds everything automatically. And this is very similar to how Docker build images. It collects the binaries and its dependencies into a file system. And if you want to understand how this script works in depth, check out my shell scripting video. I break down all these concepts there. Now that our root file system is ready, let's test this before creating a container. So we can run the same command, that is chroot, rootfs and the bin bash. So let's press enter here. So now we are inside our custom file system, and if I'm going to run ls here, it will not work because we need to set the path. So for that we can use the export command. So export path equal to /bin and $path. So now let's run ls here. So this time it worked fine. And if I run a hostname here, so all these command is working fine, which we have placed under the custom file system. But if I'm going to run the curl command, it will fail because we didn't specify while running the shell script. So that's why the binary is not there. Now let's use it to create a real container environment. So for that we are going to isolate environment just like containers do. So for that we are going to use the unshare command. So let me come out of it and clear the screen as well. So now I'm going to use the unshare command. So this is the command which I'm going to use to create a container like environment. So unshare will create a new namespaces along with these flags. So to create a separate namespaces for mount, UTS, IPC, net and the PID. So let's press enter. So now we are no longer inside our host environment. We are inside our new process world just like a container. And to verify that we can use echo $. So it will print the current process ID of this particular shell, and that is PID1. That means we are inside our container only. So now before using pivot root, we must convert rootfs into a mount point. For that we can use mount command, that is mount --bind rootfs and rootfs. So let me explain this command why I am using mount only to specify the root, because in our previous video we just used the chroot command. So basically mount --bind makes a directory a mount point, and pivot root only works on the mount points. That's why it's necessary to create a mount point for this particular rootfs file system. Now let's press enter here. So it worked fine, and let's verify the same. So mount and grep for rootfs. So as we can see, it created a mount point for this particular directory. So now let's go inside the rootfs, and this step is very important because without this step pivot root will definitely fail. So now before switching to root, let's confirm our position. So let's run pwd. So we are inside the rootfs directory under the pivot root folder, and if I run ls here, these are the directories which we have created under the rootfs file system. So we are inside the new file system, but it's not the root yet. Now comes the main step. This is how containers change the reality. So now we are going to use a pivot root command. So pivot_root dot old_root. So let me explain this very quickly. So dot means it will create a new root. The old_root means it's a directory where the old system is going to be moved. So we have already created one folder, that is old_root, using the shell script, and we are specifying the same directory here as well under the pivot root so that it can move the old system. So we are not hiding the whole system, we are just replacing the root. So let's press enter here. So it worked fine. So now it's time to verify what just happened using the pivot root command. So let's run cd/. So we are inside the /drive, and if I run pwd here, so we can see it's a /drive. And if I run ls/ here, it's not working because in our custom file system we have placed all the binaries under the /bin folder, but by default the system will look for the /usr/bin. So we need to export the path. So export path equal to /bin : and path. So it worked fine, and let's run the same command again. So if you notice, something interesting happened here. So when I run ls/, it prints the custom root file system which we have created using the shell script. So this is not the host anymore. We didn't hide it, we just replaced it. And you might be wondering why I'm able to run the export command and the pwd command as well, while I'm not able to run the ls command until I exported it using the path variable. That's because the pwd is built into the shell, but ls is an external program because we don't need to specify any path for the pwd and that's already built into the shell. So in the containers as well, built-in always work, but external binaries must exist inside the file system. Now let's inspect our original file system also. So for that we can run ls/oldroot So if you see, the old system is still accessible here. The host didn't just appear, it just moved out. So at this point, we could detach the old root. In real containers like Docker or Podman, old root is completely unmounted, so the process cannot access the host at all. And that's how containers achieve full file system isolation. So we didn't delete the host, we just changed what this process can see. Now we mount the /proc so system can behave like a real environment. So for that we can use mount -t proc and /proc. Let me explain this very quickly. So /proc is a kernel interface and it's required for process visibility. So let's press enter here and it worked fine. And if I run ps command, and we can see only 2 processes are running. So now look at this. PID1 is a bash. That means this shell is acting as the init process. In containers, your application becomes the PID1, and that's why signal handling in the process management matters. Now look at the file system. This is not the host anymore. We only see what we have created, like bin, lib, lixt64, old, proc. This is our isolated root file system. So now we have a process running in its own namespace with its own file system, and this is already a container. There is no Docker here, no Kubernetes, just Linux primitive. And this is exactly what container runtimes automate for us.
So now you have seen it. This is how container actually start. Not chroot, not abstraction, a real root switch. But we are still missing a one critical piece, that is control. Because isolation is one thing, but what controls how much CPU or memory it can use. That's where C groups comes in. In the next video, we will break down C groups and the C groups v2, the part that actually controls containers. If you found this helpful, hit like, share it with your friends and subscribe for more content like this. Thanks for watching. I will see you in the next one.